Measures of variability for ungrouped data. So we're going to look at how we can find the range, the interquartile range, the variance, the standard deviation, the z-scores, and finally the coefficient of variation. And what do they all mean? They are all measures of variability for ungrouped data, and we'll see exactly what do we mean in terms of variability. So variability describes the dispersion or spread of the data set. So how far apart are these values, or the convergence, unity of a set of data. So if you think of temperatures, let's say you have 3 temperatures, and let's say one is, say you have a temperature of 2 degrees Celsius, 15 degrees Celsius, and 30 degrees Celsius. There's a lot more variability in those 3 days of temperature than say we have, let's say we have 3 days, 15, 14, and 16 degrees Celsius. So the first set would be a lot more variable than the second set. Okay, so we'll look at different ways we can describe that variability. Okay, so looking first at the range. So this is what we call the range, or full range, is how far apart the maximum is from the minimum. So that tells you how many values it covers. So this is a data set that we used before for determining the mode. It was an example, and we have a minimum value of 35, maximum 48. So the range formula is 48 maximum subtract 35 minimum gives us 13. So we know that there are 13 values between the min and the max. Moving on to the interquartile range. The interquartile range is the central 50% of our data, right? And it is denoted as IQR, interquartile range. And you calculate it with the upper quartile, or the third quartile, subtract the lower quartile. So Q3 subtract Q1 is the formula, and it will give you that 50% of the data, the central or middle 50% of the data set. Okay, and it tells you how spread out the data is as well. And I'll let you read about the interquartile range properties. Now we have deviation from the mean. So how far are the values from the mean? And so this is another way to measure variability. If we have, say, a population of 5 values, 5, 9, 16, 17, and 18, the mean of those values, mu, is 13, because we're talking about, this is the population. So the mean mu is down here on the number line, and that's where it would be. And then these purple lines that go out from it show the distances from the mean, the values of the data from the mean. So we can see there's 2 values that are below the mean. That's the distances are 5 and 9. And so 5 subtract 13 and 9 subtract 13 give you distances below the mean. 16, 17, and 18 are distances from the mean above the mean. So if we add those all up, -8, -4, +3, +4, +5, we get 0. And this is true for every data set. You take the values of each data, subtract the mean, you will always get 0. If you do not get 0, then something has been done wrong. You haven't calculated it properly. So this here, this question mark, can you guess what that should be? So it's x subtract x bar. So x subtract x bar shows us the deviation. So how far away are the values from the mean? And that is another measure of variability. We can capture the average of those distances with the variance. And the sample variance we denote with an S, and it is the sum of each observation, subtract the mean of the values, squared, divide by n, which is the number of observations, subtract 1. And that will give you the sample variance. It tells us how far away, on average, are the observations from the mean. And they're measured though in square units. So if your data, let's say your raw data is in centimeters, then the variance would be described as centimeters squared, which doesn't really make a lot of sense. It's hard to interpret. So what can we do? We can then take the square root of that variance, and so we take the square root, that would be then s, right? If we take the square root, we get s, and we call that the standard deviation. And the standard deviation is going to be in the original units. So if we were in centimeters, we calculate the variance, that would be centimeters squared. We then take the square root and we're back to centimeters. So that's going to be each value, subtract the mean, squared, divide by n-1, that's our sample variance, and take the square root. All right, so this is easier to interpret than the variance. This measures the dispersion of the population data. If we're talking about population, the standard deviation would be sigma, and the variance for the population would be sigma squared. If we're talking about the data, the sample data, then we use s and s squared to describe the standard deviation and the variance. So that keeps the two separate, and you can use that in notation to describe whether the data is a sample or a population. So in the course textbook, there are some computational formulas that make it easier to calculate when you have a large data set and you are using a calculator instead of, say, a program like Excel or R. You can then use those computational formulas. There's one here, let's see here. So for example, one would be the sum of the x's squared. So the sum of your values in your data set, sample, this is a sample. Subtract the sum of all of them, all squared. So you would add them all up first, then square them. Here you take the square of each one. Divide by n, and then divide the whole thing by n-1. This formula works really well if you have a calculator instead of some type of computer software for large data sets. It doesn't matter though, you can use what I have in the previous slide. It's up to you. I find it easier if the data set is small, then I use this formula here for variance and standard deviation. Okay, so again, if you want the standard deviation, just take the square root of the variance. Here's an example I'd like you to try before moving on to the next video segment. So find the sample variance and the standard deviation of these 4 observations. Okay, so give this a try before moving on, and I will work through this example starting with the next video segment.